Sort. Quicksort has an average case time complexity of O of n log of n. It has a worst case time complexity of O of n squared. Quicksort is one of the more heavily used sorting algorithms because it's one of the quicker ones. When we think about Quicksort, we really want to think about it in terms of two things. One, it's recursive, and two, it uses a pivot. So what's a pivot? A pivot meets the following three conditions after we've sorted it. One, it's in the correct position in the final sorted array. Two, items to the left of it are smaller. Three, items to the right of it are larger. And I'll put a link in the description below that describes Quicksort on more of a conceptual level. So first, in order to write our Quicksort algorithm, we're going to start with writing our partition function. And we're going to call it partition for. So HOR stands for the HOR partition scheme. HOR uses two indices that start at the ends of the array, so one at the 0th index and one at the end, that move toward each other until they detect an inversion. The inverted elements are then swapped, and when the indices meet, the algorithm stops and returns the final index. HOR's scheme is more efficient than Lamuda's partition scheme because it does 3 times fewer swaps on average. However, like Lamuda's partition scheme, HOR partitioning also causes Quicksort to degrade to O of n squared when the input array is already sorted. So to start off, the partition accepts the array, a left index, and a right index. Then we'll make our pivot, which will be basically around the middle index, or it will be the middle index. And while the left index is less than or equal to the right index, we want to keep going. So first, while the left pointer is less than the pivot, we want to keep moving the left pointer up. And then while the right pointer is greater than the pivot, we want to keep moving the right pointer down. So this is setting us up to basically find the 2 pointers that we want to be swapping. Then, if the left pointer is less than or equal to the right pointer, then we want to switch and then move the right pointer up by 1. Sorry, the left pointer up by 1 and the right pointer down by 1. So if we're going to use ES6 to do the swap. I just personally find the ES6 method of doing swaps in arrays so much cleaner and easier. We're going to increase left by 1, and then we're going to decrease right by 1. And then after all of that is done, then we want to return. Okay, now let's go to Quicksort. For Quicksort, left will either be left or it will be equal to the 0 index if nothing is passed in, and right will either be equal to the right parameter that's passed in or to the array length -1. So you could write this inside of the parameter here, but I'm just going to write it here to make it more explicit. Next, we'll get the pivot by calling the partition function with the array left and right. A partition function will move the left and right pointers and then swap them when appropriate, altering the array, and then return the left index. All right, and now is the recursive portion. So if the left index is less than the pivot minus 1, then we want to recurse and call quicksort on that portion of the array. And conversely, we want to recurse on the right side of the array. And when the entire array is sorted, when neither of these are true and we've reached our end condition, then we want to return the array. Give this a try to see if it works. As you can see, Quicksort sorts the array that we have. And there you have it.